Have you ever really thought about how we get power from a spinning turbine? Or why your phone charger can power up your device without any moving parts? Well, it all goes back to this one single, elegant discovery in the 19th century. It's the moment we figured out that a simple magnet could actually create electricity. And this isn't just some dusty science lesson. It's literally the origin story of our entire electrical world. Okay, let's dive right in.
So, here's our roadmap. We're going to start with the fundamental experiment that kicked this whole thing off. Then we'll unpack the physics behind it, see how it led to world-changing inventions like generators and transformers, and finally, we'll touch on how this simple idea helped inspire one of the most profound theories in all of science.
All right, let's get into it. Section 1. A current from a magnet. We're heading back to the 1830s, a time when scientists knew electricity and magnetism were related, kind of like cousins, but they hadn't yet figured out they were actually twins.
See, everyone knew that an electric current could create a magnetic field. That was old news. But the reverse? That was a huge puzzle. Could a magnet just sitting there create an electric current? This was the driving question for pioneers like the great Michael Faraday. To find the answer, Faraday built this device that was just brilliant in its simplicity. So picture this. He took an iron ring and he wrapped two totally separate insulated coils of wire around it. The first coil, the primary one, he hooked up to a battery and a switch. The second one, he connected that to a galvanometer, which is just a fancy device that can detect even the tiniest electric currents. And remember, these two coils aren't touching at all. Now this is where it gets really cool. When he closed the switch, current flowed through that first coil, creating a magnetic field, but nothing happened in the second coil. Well, not at first, but right at that instant he closed the switch, the galvanometer needle jumped. And then, when he opened the switch, it jumped again, but in the opposite direction. And that was it, the eureka moment. It wasn't the steady presence of a magnetic field that mattered. It was the change. That sudden creation or sudden collapse of the magnetic field, that was the spark that literally changed everything.
Okay, so a changing magnetic field creates a current. But how do we describe that? How can we actually measure it? Well, that brings us to Section 2, Unlocking Magnetic Flux.
To handle this, physicists came up with a concept called magnetic flux. The easiest way to think about it is like you're counting the number of invisible magnetic field lines that are passing through a certain area, like a loop of wire. The more field lines poking through that loop, the higher the magnetic flux. Simple as that. And this idea led to one of the most important equations in all of physics, Faraday's law of induction. It tells us that the induced voltage, we call it electromotive force, or EMF, is determined by a couple of key things. First, you've got N. That's just the number of turns or loops in your coil. More turns, bigger effect. Easy. Second is this part, delta phi over delta t. Now, don't let the Greek letters scare you. That's just the physics way of saying how fast the magnetic flux is changing. So it's not just about the change, it's about the speed of the change. The faster you change that flux, the bigger the voltage you're going to get.
Now, you might have noticed a little minus sign in the full version of that equation. That's not just some mathematical quirk. It actually represents a really deep principle of nature. So let's move on to Section 3 to figure out what's going on. Lenz's law, or as I like to call it, nature's pushback.
What Lenz's law basically says is that nature is, well, it's kind of lazy. It doesn't like change. The current that gets induced will always flow in a direction that creates its own magnetic field to fight the very change that created it in the first place. It's like nature is always pushing back, trying to keep things the way they were.
Let's make that real. Imagine you're holding a magnet, and you push the North Pole towards a coil of wire. As you get closer, the magnetic flux through that coil increases. Lenz's law says the coil is going to induce a current to fight this change. And how does it do that? It creates its own magnetic field, with its own North Pole facing your magnet actively pushing it away. You can literally feel the resistance.
And this is why that minus sign is so incredibly important. I mean, think about it. What if the induced current helped the change instead of opposing it? You could give the magnet a tiny little nudge, and the coil would just suck it in faster and faster, creating more and more current for free. Boom! You'd have a perpetual motion machine, a source of infinite energy. Lenz's law is just nature's way of enforcing the conservation of energy. There's no free lunch in physics.
Okay, so we've got the core principles down. But what can we actually do with all this? Well, that brings us to Section 4, generators and motors explained. These two devices are basically the workhorses of our entire modern world.
And what's amazing is that they are fundamentally two sides of the exact same electromagnetic coin. A generator takes motion, mechanical energy, and uses induction to turn it into an electric current. A motor does the complete opposite. It takes an electric current and uses magnetic forces to create motion. Motion to current, current to motion. That's it.
A generator is just Faraday's law in continuous action. You use some force, like wind or steam or falling water, to mechanically spin a coil of wire inside a magnetic field. As it spins, the magnetic flux passing through it is constantly changing, from maximum to minimum and back again. And that continuous change induces a continuous alternating current. This is how we generate pretty much all the power on the planet.
Now, a motor just flips that script. We pump current into the coil, and the magnetic field pushes on that wire, creating a torque that makes the whole thing spin. But here's the really neat part. As that coil is spinning, it's a conductor moving through a magnetic field, right? So it also acts like a tiny generator, creating an opposing voltage we call back EMF. That's Lenz's law, right there inside your motor, pushing back.
All right, let's talk about one more piece of essential technology. It's so common we don't even think about it, but our entire electrical grid would be impossible without it. Section 5, Transformers, powering our world.
Believe it or not, a transformer is basically Faraday's original experiment, just perfected. Its whole job is to step AC voltage up or down. You've got your primary coil and your secondary coil on an iron core. An alternating current in the primary coil creates a constantly changing magnetic field. The iron core is brilliant because it channels almost all of this changing flux over to the secondary coil, which induces a brand new alternating current in it. There are no moving parts, it's just pure, elegant induction.
And the magic is all in the math, which is actually super simple. The ratio of the voltages is directly proportional to the ratio of the number of turns in the coils. So if your secondary coil has, say, 10 times more turns than the primary, the voltage gets stepped up by a factor of 10. But, and here's the key, remember conservation of energy? Power is voltage times current. So if you step the voltage up, the current has to step down. This simple trade-off is the secret sauce for our entire power grid. We can crank the voltage way up for long-distance transmission, which forces the current way down, and that dramatically reduces the energy we lose to heat in the power lines. So far, we've seen how induction literally powers our world. But the story, well, it gets even bigger. Section 6, From Induction to Relativity. This simple tabletop phenomenon held a clue to the very nature of reality itself.
Think about this. You get the exact same induced current whether you move a magnet towards a stationary coil or you move the coil towards a stationary magnet. All that matters is the relative motion between them. This weird symmetry just fascinated a young patent clerk named Albert Einstein. In fact, he mentioned it in the very first paragraph of his groundbreaking 1905 paper on special relativity.
And what this all ultimately revealed is something truly profound. Electricity and magnetism aren't actually separate forces. They are two sides of the same coin, two different ways of looking at a single, unified electromagnetic force. A moving electric charge creates a magnetic field, and a changing magnetic field creates an electric field. They are completely and fundamentally intertwined.
And that kind of leaves us with this final thought. A simple experiment with a magnet and a coil of wire didn't just give us our modern electrical world, it also pointed the way to a much deeper understanding of the entire universe. It just makes you wonder, what other fundamental connections like that are just sitting there, hiding in plain sight, waiting for the right person and the right experiment to reveal them?